Okay, hello everyone. Can you see well my screen?
Yes.
Yes, okay. Well, thank you very much for the introduction and for the presentation. So today I'm gonna show some type of contourites and the processes that form them that might be a bit more different to what most of us have in mind when we usually talk about contourites. Because, well, contourites are typically defined as currents formed by the deposits formed by the currents that flow along slope and form these large contourite drifts that we find along many continental margins. But actually, in the official definition nowadays, we consider any kind of bottom current affecting the seafloor can also generate contourites. So in the ocean, we have many different processes. Of course, we have the along slope currents related. Yeah, so they are mainly related to the thermohaline circulation. But we also have many other processes that affect at the shorter time scale. So we can have variations of currents daily related to internal waves, for example. And they also tend to affect smaller areas on the seafloor. So the question that we pose to ourselves as sedimentologists is actually, well, from all these processes that we can find in the ocean, what is really controlling sedimentation, seafloor geomorphology, and what is affecting the currents in different time scales that will be what is actually going to be recorded in the sedimentary record. So when we talk about a contour depositional system, we can have many different structures at different scales. So first at the large scales, several kilometers scale, we can find, for example, plaster drifts and related contourite terraces, and they tend to be formed by long-term processes related to the thermohaline circulation. But if we look a bit more in detail at higher resolution at these structures, we start seeing some small channels, some ripples, some bed forms, and then we start having more and more information from this kind of deposits because, well, technology gets better and we manage to image in different environments already more resolution the seafloor. And these deposits are typically formed by internal waves and other high frequency processes. So internal waves are very often related to tides. So when we have the transformation of the barotropic tide interacting with the topography, then this can generate some baroclinic tides that will propagate in different ways in the ocean. So for example, when we have the formation and the critical slopes of rays of internal tides that will then propagate across along the ocean, they can also form nonlinear internal waves that will propagate around pycnoclines, and you can even see them very often on satellite images when they are propagating near the sea surface. We can also have them when, as a leeway formation, when there is an interaction with an obstacle. That's very typical in straits, for example. And then when we have the ebb and flood currents, this can generate on the top of the seal some internal solitary waves that will propagate and at some point will break on a slope. And we see in many environments this interaction of internal waves with the seafloor. Here's an example from Northwest Ireland in the Rockall Trough. You see here with a sub-bottom profiler, we have a contourite terrace and a small drift, so a terrace drift system. So the whole slope has several of these terrace drift systems, and we could see how an internal wave was breaking exactly on the top of the terrace. So we think that this interaction is also remobilizing sediment from the sea floor and helping the formation of these terraces. We also had at the same time a CTD profile with turbidity measurements in the same location, and you can see also how in the area where we see these higher amplitudes in the water column, we have more particles in suspension. So we have the generation of nepheloid layers, so zones of water in the water column with high amount of particles in suspension that remove sediment from the slope and take it further to the open ocean. And these waves are actually really big. In this case, over 100 meters of amplitude, so it's much larger than this the Liberty statue. And if we compare it with the largest waves that we can find on shore, so it's the very famous Nazare wave, where these giant waves are served by some very courageous people over there, but they reach only up to 26 meters. So here we are talking about even almost 4 times larger waves that are gonna break in the seafloor and create very strong currents also at the seabed. And so there was a study that simulated this interaction. And here you can see how internal wave propagating in the pycnocline breaks on the slope, and in color is the sediment density in suspension. So you see a current that moves upslope, that some boluses that keep propagating upslope, and then the material gets trapped within the pycnocline, and we have the formation of a nepheloid layer. So you can imagine that the same time that all this material is being resuspended, we are going to have also the formation of some particular structures at the seabed. And this has been observed in many different measurements of the water column. Here, echo sound image simulates, shows a very similar feature as was simulated in this study. Also, we had recently a cruise offshore Mauritania, and we observed again very similar features in the upper slope and shelf edge. So here, what you see, this is the water column. We have a nepheloid layer that starts at around 300 meters, 300 to 500 meters with the depth, and then it propagates offshore. And in the zone of degeneration of the nepheloid layer, we have a field of bed forms. So we have first scours, so we have erosional features in the deeper part, and then in the upper part, we start having a field of bed forms. And here in the sub-bottom profile, you can see how these bed forms that are quite large, several hundreds of meters in wavelength, they migrate upslope. And interestingly, also below this zone of generation of nepheloid layers and these bed forms, we have a chain of, or 2 chains of coral mounts. And actually, it's a very typical combination that we tend to find bed forms and erosional features in zones where we also find coral mounts, because cold water corals, they need particles in suspension, so here they get everything they need from the interaction with the internal waves. So at the end, this interaction between internal waves at this seafloor generates nepheloid layers, so we have a lot of material in suspension, also creates some particular bed forms, some sediment waves migrating upslope generally, but sometimes we can also find erosional features. These kind of bed forms have been found in many different environments. For example, also in the Messina Strait. Here we have the generation of internal solitary waves at the seal, and you see them propagating northwards here. And in the zone right at the seabed, in this area, there is a field of sediment waves, dunes in this case. They are made of sand, and they are also moving in this direction. So it has been suggested that they are formed by the interaction with internal solitary waves. Similar also in the South China Sea, there are some huge fields of sediment waves and erosional channels, and it has been suggested that they are related to either internal solitary waves that are breaking on the slope and interacting with the slope, and also internal tides that are creating currents up and down in the area, and probably the diversity of erosional features, orientation of the bed forms, and also direction of migration of the bed forms depends on how these waves are going to interact with the seafloor. And this depends on the type of wave, but also on the seafloor slope and seafloor morphology. In the Mozambique Channel, we have more examples. Here there is in the upper slope a field of dunes. They are made of sand. You see also here covered by ripples, and they migrate upslope, and they decrease in size also upslope. And before the dunes start, so further downslope, we have an erosional surface. So all of this indicates that we have a current going upslope related to this interaction with internal waves that is generating these bed forms. But you can see here in the topography that actually there is a main crest, but we also have some other orientations, the secondary ones a bit smaller. So probably it's not always going also upslope, but we might have some reflection in a different direction that can generate some secondary dunes. In the same area, but of the margin, but a bit farther south, instead of having a field of dunes, there is a huge channel. And this channel is located in the upper slope. You can see here extends over several kilometers. It's relatively small, but this is there. And the interesting thing is that actually we have a similar one preserved in the sedimentary record. We can identify it here very well in seismic. And we know that it was formed during the last interglacier, because in the area, this area is in front of the Zambezi Delta. So during the low time, we have a very high sediment supply, and the currents, even if we have internal waves and the currents are still strong, if we have too much sediment supply, they are not going to be able to erode so efficiently the seafloor. So we tend to have these erosional surfaces during the periods of relatively low sediment supply. And the idea that we have why we might have such a continuous and straight channel, there is no obstacle, it's just in the middle of the slope. You see here it's just continuous and suddenly a channel. So the idea is that probably we have an internal wave coming, but in the area we also have barotropic currents, barotropic tides that are gonna be affecting the area regularly in a different direction. And we speculate that probably what happens is that when the internal wave is approaching, and we have also the tide, the barotropic tide coming from the shelf going in the opposite direction, it might stop the wave for a while in the area, and that could make that it's always breaking and affecting the slope for a longer time in the same place, generating focused erosion and not just a broad erosion on the seafloor. In Namibia, we also observed the interaction of internal waves with the seafloor. Here is again a zone with abundant coral mounds. So you see here now we are in the shelf, mid to outer shelf. And here you see in the lower part a lot of erosional surfaces and several mounds that are formed by cold water coral mounds. And here is a huge escarpment and channel that extends along several kilometers and is again very straight. And in the zone of the channels of the mounds, you see also some channels that are oriented across the slope. So these mounds, the coral mounds and the channels, were modes and drifts. So you see here some modes along the ridges of the coral mounds and some drifts in between. They are oriented across the slope. So actually these features are not formed by a long slope currents, but rather by internal tides that move across the slope every day. So in addition to that, there are internal solitary waves that we can even see from satellite images approaching towards the shelf. And we could image with our parasound data how they propagate in the water column. So you see them, these are the same time as the cruise, both images. So you can see these internal waves approaching, and then we can see how they break here at the escarpment, where we have this very big erosion. And concerning sedimentation, actually the area where we see this strong interaction of internal waves and the seafloor, we have coarser material and also less organic matter. And we find in between, so in the areas that are a bit calmer without such a strong interaction, we have mud depositors and more accumulation of organic matter. We have also some seismic in the area, so we can prove that these channels and this escarpment and erosional surfaces are not related to any tectonic structure. You can see all the units below them are completely continuous and no tectonics going on. So we know that it's all related to sedimentary processes. There are no submarine channels either in the area, no turbidites that can be found. So we think that the role of internal waves in this case must be very strong. The sediments, we have also some analysis of surface sediments in all the area is mainly muddy sand to sandy mud, and it looks a little bit like that with still quite a lot of some fine grain material in there because it's a zone with very high productivity in the surface, so we still have some accumulation, but this is what generates at the end, gets resuspended by the interaction with internal waves and will generate the nepheloid layers. So we have also some turbidity measurements of the water column, and we can see that in this zone here below the escarpment, where we have the coral mounds and these across the slope modes and channels, is where we see also in the water column some nepheloid layers coming out of this region. And you see again in this case the internal waves approaching the escarpment and then breaking here, making like a hydraulic jump, and probably this is also enhancing over time the erosion in this area and making this escarpment and channel larger and larger over time. We also have some measurements from a short-term lander that was situated on the top of the escarpment, and we could see, we also have some turbidity measurements, and we could see some changes in the turbidity. And these changes, these peaks, very fast changes in turbidity, they were always linked to strong changes in the direction of the current. And interestingly, it's not necessarily the moment when the current is the fastest. So what we interpret from here is that probably this is also related to the interaction with the internal waves, because we are going to have different processes moving, and as we saw in the simulation before, this is based on this previous simulation studies, when the internal wave approaches and breaks, we are going to change the current direction. Usually it starts with a depression wave, so the lower part below the wave will move basinward, but when it starts approaching the slope, the wave is going to change to an elevation wave, and in this case the zone, the water below that is in contact with the seafloor is going to move landward, and this is the moment where there will be also more turbulence and more mixing in the water that will enhance seafloor erosion and favor sediment resuspension and finally generate the nepheloid layer. Yeah, so to summarize, we are going to have very different type of deposits and processes depending on the scale at which we are looking. So if we are looking at a basin scale and large scale features like the large contourite reefs, large moats, and in general large contourite depositional systems, then we will be able to see rather changes in the thermohaline circulation. So we will be able to see what are the long-term changes in the bottom currents. But when we start getting a bit more into the smaller scale processes and products, so even in the seismic, sometimes we already start seeing some of them that we can identify erosional features, we can have a small scale bed forms, dunes, and even if we look at the core scale, it's probably part of this is going to be recorded in there. And here is where other smaller scale processes and also that might act at higher frequency can be very important in their formation and should be also considered. And even though they might be smaller in scale and also acting at higher frequencies, they can be preserved in the sedimentary record, and they should be also taken into account. That's why, in my opinion, it's very important to know in which areas of the seafloor we can expect such an interaction, so that it can be integrated in a proper way in conceptual models. Yeah, and that's everything from my side. Thank you very much.
Thank you. That was a fantastic talk. If there's any questions, feel free to, I don't know if there's a raise their hand thing here, but just unmute yourself and ask a question. We've got about five-ish minutes for questions, and then we'll move on to the next talk. You can also just type them. But while we wait for the questions, I think one thing that was so interesting about what you showed already is just even some of those images you were showing of the Mozambique Channel, of offshore Mauritania. When you think of the range, the spatial, how quickly some of those bed forms were changing in space, I think it's pretty interesting to think about. Of course, what gets preserved in the rock record, but then as we're looking at outcrop analogs of these things, right? It's often easy to think, hey, let's keep what's happening across this outcrop to one process or to one style of bed forms. And just to think of, especially the Mozambique Channel one, I think that surprised me, just how rapid it was going from an erosional surface to dunes, to then dunes that were decreasing in sizes, and just thinking about that in the outcrop space. And then also, when you're showing that range of geomorphologies on the slope, again, understanding the long-term implications of alternative deep water systems interacting with that, but just thinking about how turbidity currents might interact with that pretty complex slope being, or slope alteration simply due to just one of these processes that you're talking about. So I think that was pretty fascinating.
Yeah, thanks. A great summary.